Well, here's our whole team, plus more. My name's Carol Song. I feel I'm really a minority here, because I'm a computer scientist. There are only a few of us here. But it's very interesting to hear about applications, to hear about what the needs are, and that's where we come in. So this project, you can see there's a long list of people, and there are more people actually working behind the scene. I'm going to give a quick overview of what this project is and what we have done. And it was a National Science Foundation funded data interoperability project that the funding, the award was made in 2008, but we actually didn't start until pretty late. And it's pretty obvious that we have a very multidisciplinary team, and as you can see, a couple of us are from the what we call the research computing arm of Purdue's central IT, and we help build the cyber infrastructure pieces. And we work with the domain scientists from civil engineering, from agricultural biological engineering, and agronomy and EAS. And we also have computer science faculty that are part of the team and help with the visualization aspects of things. So when we proposed the project, we had some tools and systems around us that we were aware of and using, and we sort of built on top of those things. So obviously, pretty much everybody knows the U.S. Drought Monitor that gives a weekly update of the drought conditions. And in Indiana, there's also the policy for drought declaration based on the Palmer Index. And I was told that there was a big drought in the 80s, and that was how the state came up with the process to make the declaration. And then also we have various people on the team and also their colleagues in the departments that work with many groups that's related to agriculture, such as crops, and also the weather people. And we constantly get feedback from them on, it would be nice to have the information in this way and that way. And also at that time, Purdue developed technology called Hub Zero that was coming into maturity, so to speak. It's a cyber platform or a web platform that enables scientific online simulations and collaborations among researchers. And it was originated from a project funded by National Science Foundation for nanotechnology simulations. And out of that whole development, that team extracted the software and formed this Hub Zero core, which represents the generic software that you can set up and use to build your own community, to put your own tools into it. So, so this DRINET project we started by building on top of those technologies and the things that we were sort of doing. And our goal was really to bring the computational infrastructure into study of drought. And we have people who are very good modelers. We have people who have the outreach to stakeholders. And now we were looking at a piece which it turns out to be the cyber infrastructure, to be the computational infrastructure that ties things together in the hope that we're going to deliver tools and data and information in a way that would meet the end user's need. Some of the science questions, so when you write these NSF proposal, they always ask you about your science drivers. So these are the questions we posted, and we're still working on all of the aspects here. One that I would like to point out is we're looking at what additional data that goes beyond just the traditional hydroclimatic data sets that can also provide useful information on drought onset and impacts. So we're looking at especially the data aspect. And with the team, with the multidisciplinary team, everybody has a specific direction, research direction that they are already working on, or they're exploring new directions. And then together, we build the research results and also the cyber infrastructure pieces into this platform we call DRINET. So our presentation is going to be very hectic because I'm going to drag people in so they can show their faces, not just me. I'm going to talk real quickly about the cyber infrastructure aspect of this project, show you some online interactive tools and data sets, how we integrated them. And we're going to have a couple of our co-investigators coming up here. Each has about 3 to 5 minutes to zip through their content. So the DRINET cyber infrastructure is based on the Hub0 platform, which if you look at in simple terms, the user can get in touch with is actually the web page. If you say, a lot of people say it's a website, it is. But it has some distinctive features that are well suited for scientific investigations. The number one, I would say, is the online interactive tools that you can integrate. Now you can say you can probably find a good programmer to put your tools online, but that typically takes a long time to do, a lot of effort in software development. The Hub0 platform gave us some tools to make that process easier. So if you have a code that you want to share with your colleagues, you can write a wrapper that generates a graphical user interface automatically for you, and when you publish it on DRINET, it'll become usable by other people. And there's no software downloads, no messing around with installing different components on your computers. And also, to make it easy for people to share data, share information, and also participation. So you don't, for example, you want to host some of your contents here, you don't need to go through a sysadmin, which people usually try to stay away from. And the other feature that we found many projects they all like is this concept of one-stop shopping. You go there, you can upload your data, you can share your data, you can organize your groups to collaborate with each other. Because the Hub0 was originally developed by the nanotechnology groups that have a need to do these simulations. Some are significantly computational intensive. Most of them had very small data. You open up a user interface, you enter some input parameters, and you get an output. And so to use it for our DRINET project, we actually have to do a lot of additional development to put in expanded capabilities, such as to access data remotely in a distributed fashion, to allow people to publish their data sets on their own without us to be in the middle, and also to enable geospatial data, for example. So those are some of the things we have put in there. So I'm going to move away from the PowerPoint. That's the wrong browser. Okay, so if you go there, it's open to everybody. On my small laptop, the fonts looks a little weird, but you kind of have the general idea that the resources on here. So the first thing I would like to show is a model that's developed by one of our co-investigators, and it's a probability-based, HMM-based drought index viewer. And you can get to these resources if you go click on tools, and you see a bunch of these things. And every one of them has some explanations, and we're still because this is still for research, so we haven't gone into a lot of effort and time putting in documentation, but there's enough so you understand what it is for. And so in this tool, you can go to any of these stations. You can see the data we have that really goes back many, many years ago. To me, that seems a long time ago. So I don't know which year, that would be interesting data. So let me just try this. And you can simulate, number of years. And there's a time window that is to say, drought happening in that 1 month. Or you can change it to 3 months. And it does the computation in the back and using the hidden Markov model that GS and his students developed. And here's the output. On the top part, you see the HMF-based drought index, which gives you the probability of how likely drought at a certain level will happen. So you can see different colors in one of these timestamp. And on the bottom is the standard SPI index. And in this case, you can see that because SPI is not probability based, it just shows you this is D0. And here, with this method, you see that the chance of having a D2 drought is about 60%, while having a D1 drought is less probability. And you can see similar places in at various time. And so it incorporates a level of uncertainty, and how you make use of that's still a research question. And how do we convey this type of information to users? That's still, we're still working on those issues. And let's see. So another type of tools that we have is, this is our latest work that we enabled geospatial data access into the hub. And so here you can see that this is a data set that includes crop information. So it's a global scale, it's on the country level. And here that I'm pulling up the maize yield information. And this is, I don't think this is the problem with our tool, it's just the data set didn't have much data in there. So if you look at certain countries, and that gives you the location of that country, and then, or the location, there are many points in there. That's the point that I was clicking on, and here's the yield information. And one thing that we really, is one of our major goals from a cyber standpoint, is to really link, not just have static data for you so you can look at it and download, probably plot, but also associate that with the tools that you can actually run against the data. In this case, it's a real simple application, and it's a weighted average of yield, or I forgot what it was. Somebody uploaded, okay? So that's why I'm not very familiar with. So in this case, you can see that there is one tool that's associated with the data set, and when you bring it up, you can see that there are actually two programs. One was written in GRASS, and one was written in R. And so if you want to look at what it does for people who knows what this language is, and you can easily go in there and check it. And so without really downloading things and install R and GRASS yourself, you can run this model online, and it'll take a little bit. This is a really quick one. Okay, and after that computation is done, then you can view the results. In this case, it's a scatter plot that we chose to print, and you can look at the data points and see what's actually represented. And so that's a geospatial data enabled tool. And as far as data, we also integrated multiple data sets into this platform. And this one is the latest one we put in. So on the right-hand side, you can see that I can check different stations, and for each of these, you can look at the, sometimes it's really hard to, I think these dots are too small. I don't know. So again, the idea is interactively, you can, instead of, you got to download the whole thing down to your laptop and then try to sift through the data, you can select where you want it. You can also, on the right-hand side, you can see that you can enable a selection of a whole bunch of stations. And in this case, I'm just interested in looking at one station. And I know that if I plot that many years of data, it'll take a long, long time. So I'm going to make it really quick. So this is how the data is presented. There are different ways you can format this and download this. And so that's one thing. I gotta watch my time. Okay. And we also have tools for data publishing. And I know John, my good colleague from DRINET Project, John talked about the DataNet, and I'm sure they have some wonderful tools too. And I hope at some point we can collaborate on some of these things. So this is what we call iData tool that allows people to upload data. And so from the interface, it looks very simple. And you can see the shared collections that people have published and share with you. And you can also publish your own data. Now behind the scenes, some of the data, if we manage the file-based data in distributed data repository. So one of the repositories we're using is a DRINET data repository. And you can also upload tabular data. I know a lot of people have those type of data that, like a spreadsheet, you can, there are ways for you to upload. And we haven't put out tutorials or anything like that, but we have been working with some students like Rashad there, and this latest data set about Messy Creek, he's done this just recent weeks. So we hope that many people find that to be useful. Let's see. One last thing, people, one of our ideas was to use this platform to engage people, not just researchers, but also eventually to the community, to stakeholders. And one of the ways that, that people can use it to collaborate is to create your own project groups. So this is one example, because it's a nice one, so I'm showing this. And it's not part of the DRINET project, but somebody who has an interest in the tools that we've developed. So they're using the site to coordinate their activities. And so you can see there are all these your familiar tools, wikis, blogs, forums, things, but that's just within your group. And you can set the levels of sharing that you want, you know, the information to be seen by the public, anybody who visits the site, or only to certain groups. So, so that's a quick run through of some of the things. I gave you some examples of things. Now, how do people use that? How do these things help the researchers on our team? I'll let my co-investigators talk about those things. Let me bring back this slide. Let's see, here? No, went too far. Okay, here. You can just use these, or you want.
All right, I'll just go ahead and use this. I only have 2 slides. So hi, my name is Jake Carlson, and I'm with the Purdue University Libraries. And if Carol feels like a minority here, I think I'm a super minority. I don't think there's any other librarians here. But I've been involved with DRINET from its start, looking at metadata and how metadata fits into this larger system that we're developing. Metadata is very important. It adds functionality to the data sets, and particularly our needs for DRINET with regards to the metadata were to enable discovery, so to enable people to search through DRINET, to browse through DRINET, to find data sets that are in here. To provide description, so once you have found a data set, can you understand what this data set is, and can you make appropriate use of it? So it needs to have that information there to be sure that you're generating data that you actually expect and need for your purposes. The metadata is designed to help define relationships between different data sets. If you think of a library, we don't just buy books, we develop collections of materials, and we have ways of organizing those collections appropriately in the library to add utility and add value to the resources that we have. We want to apply that same kind of concept to data here. So how can we make connections between data set A and data set B to help people really get a sense of what our collection consists of in the DRINET environment? And then also we need metadata to help dissemination. So beyond just dragging people to DRINET and having them search and discover data in that environment, can we export our data, or our metadata rather, both to systems like Data One described earlier today in terms of metadata aggregators to help people find data sets that are in DRINET outside of the DRINET environment, or even to Google and other search engines, again, to add utility and to add dissemination to the data sets in DRINET. So, but there's a number of challenges with regards to developing metadata for a system like DRINET. And I think you've heard some of these earlier today. There's a real diversity of data that is needed to study droughts. Drought isn't just climate data, it's not just precipitation data, it's not just air quality data. It also may involve things like economic data or medical data or other sorts of data that have to get filtered in and connected to other data sets to add value and purpose for what we're trying to accomplish with DRINET. There's a diversity of audience and a diversity of needs attached to those audience members. So again, it's not just climate researchers or hydrology researchers. It's also folks who are in the field, who are practicing, who are part of government agencies or other efforts. It's farmers, it's crop growers, it's educators potentially as well. So there's a diverse set of audience potentially for DRINET, and they all have their own particular set of needs that they're going to come to DRINET seeking to solve or to address. And there's a need for balance between the depth and the breadth of metadata. Certainly we want as much metadata as possible to add a richness so people really get a sense of what this data set is and what it contains. But if we ask for too much, folks who are uploading their data sets are going to balk. They're not going to do it. So we need to be sure that we have a balance between what we're asking folks to provide and realistic expectations of what they're able and willing to provide us. There's also a need to provide a balance between standards and local needs. So metadata standards enable a lot of the functionality that I just described. Adhering to a particular practice or particular way of setting up the metadata enable things like dissemination and discovery. But if we're too rigid in a standard, we're going to miss addressing some local needs that are very important for the DRINET group. So we need to be sure that while we're adhering to a standard and enabling the kind of functionality we want, we're also accepting and open to local needs to ensure value and utility for our users in DRINET. Go ahead and go on. So after looking at a number of different possibilities for metadata standards, I came across something called the Directory Information Format, or DIF. And that's produced by NASA, the Goddard Space Flight Center, and primarily applied to the Global Change Master Directory service that they provide. Essentially, this is a directory of data sets, multiple different types of data sets, mostly pertaining to climate and earth science. But in looking at the metadata standard itself, it seemed broad and flexible enough that it could potentially apply to other data sets as well, which is why we selected it as sort of a foundation for looking at how we might address metadata with DRINET. And the next stage for us is to figure out how to implement that in the DRINET environment. If you notice where Carol went through the iData publishing tool, there was a section that said metadata. We've got the basic fields in place now, and we need to keep on testing and keep on generating metadata records for what we have in DRINET. And with that, I'll turn that over to GS.
It's somewhat unfortunate. We are the hosts and we are going to run over, and I'm the one moderating this session. All right, I'll go through it quickly. I think Carol showed you some of the tools that we have on the DRINET website. For some of the tools, the data that we have used are the actual precipitation data from the various stations, or we have used unregulated stream flows for drought analysis. So this just shows you some of the locations. And if you were to go to the DRINET website, you would essentially have all this data, even the raw data, available to you. So one of the things that we developed was a joint deficit index, which is like another index for characterizing droughts. We have several of them. However, this has the advantage of essentially trying to combine information over longer time periods in a probabilistic fashion, and therefore it is a joint deficit index. And if I were to look at if I were to go back and see how the joint deficit index evolves for, let's say, past periods which we know to be droughts, we would see some sort of a time frame. In this case, we are marching in months. The 1930 to 1931, that part of animation is not working for some reason. And then the joint deficit index, we have tried to color code it to look similar to the US drought monitor. So blue means wet, dark brown to red means extremely dry conditions. And as you cycle through, you can see that the JDI is going to change. You'll go through extremely dry conditions in the drought and eventually recover. Or the 62 to 64 drought, again, you can cycle through and see how the drought or the JDI index, and therefore get a perspective for how the drought is evolving in time. Okay. Now, so that was just an index, and what we can do with this index, this is an example. Let's look at the 1988 drought, and I'm using a 1 month time frame as an example. You can choose 3, 6, 9 months, and so on. We can essentially ask ourselves the question, how much precipitation will be required to return to normal conditions? And what you would find then in this severe drought condition is, for July 1988, most of the state you will require more than 7 inches to fall in that one particular month, which tells you how deep or how severe that drought was. And we can also calculate the probability of that happening. What is the chance of recovering from that drought? And as you see in this case, the chance of that happening, the recovery is very low throughout most of the state. And we can therefore make these projections of water deficits and probability of recovery at various time points and for various time frames, 3 months, 6 months, over a growing period and what have you. And then what you would like to do is be able to use this information, projected water deficit and its probability of recovery, to figure out how we should assess impacts and so on. Okay. I think Carol already talked to you about this probabilistic drought classification, and this is just another example where this blue line that you see is essentially the rainfall data. The probabilistic classification essentially addresses model uncertainty. Right now, if you go to the drought monitor, it says, okay, drought class is D3, but we have no idea of what the uncertainty around that is. The probabilistic classification actually gives you, in this case, using the height of the bar as what is the probability of it being in a D3 drought versus a D2 drought or a D4 drought. Okay. And it also gives you much smoother transitions than the SPI does, as was talked about by the previous speaker with the blended drought index. Okay. So these are just some examples of some of the tools that we have worked on and put up on the DRINET website. And Indrajit will come and talk about water quality aspects.
Is my time up? My name is Indrajit Chaube, and I'm professor of agricultural and biological engineering. One of the areas that is likely going to be impacted is water quality. And we are trying to look at what could be the water quality impact. Okay, so wrong computer here. What you see here is 4 of the water quality parameters that are widely used to evaluate water quality of a stream or a river. On top left corner is the phosphorus, below is atrazine, that has a very strong seasonal signal. It happens only during crop production or early part of the crop production when the corn is planted in Midwest, and that's when atrazine is applied. Ammonia that may be coming from organic or inorganic fertilizer applications or from wastewater treatment plants, and E. coli, a common bacteria that is of great health concern. So we wanted to look at, is there any signal coming from drought conditions versus wet conditions in river water quality in terms of these 4 indices. And what you see is some kind of signal where in this particular water set that is dominated by agricultural land use, the concentration during drought conditions is much lower in general than concentrations during wet periods. We also try to look at how does it relate to SPI and concentration for phosphorus and ammonia on the left and mass of the loads, because sometimes in terms of the water quality, load is very, very important. Lots of times while the goal is to reduce concentration, the watershed management plans are written to reduce the absolute load of these constituents. And we see some correlation where the concentrations are lower during drought periods compared to wet periods, but you see a stronger signal for the loads for obvious reasons, because the stream flow is much more impacted. This is just one snapshot in what water said. There are many additional questions that we are trying to look at. One of the challenges is water quality data is very sparse, very limited, because it is so expensive to collect. In this case, this is one of the best monitored water sets in Indiana. We have only 11 years of data. It's certainly not enough. So how do we handle with a challenge like that? How can we bring some of maybe modeled results and start looking into that? And one challenge that we are facing that Professor Vijay Singh talked about in the morning, if all biofuel scenarios are incorporated, if I remember your numbers right, 180 cubic kilometers of water will be needed. Probably we don't have that water, so how would the yield be affected, and then how would the water quality be impacted? Those are some of the new things that we have started to look into. That's all I have. We have got Dave.
Right, so what we were trying to take from there, looking at the water quality aspect, was to start looking into some of the atmospheric aspects of the droughts. And this DRINET project provided us with that opportunity. One of the first things that we had was we had a good sense about monitoring that is going on in terms of the rainfall measurement, but not with sufficient spatial resolution as we are trying to understand the processes. So one of the projects that we have been very heavily involved was this development of a community network, like we heard about it from the bird migration perspective. The same thing is a COCORAS. Several of you might be aware, but this is a community volunteer effort where people measure rain gauge data, provide this rain gauge information, and that has been something we have used quite routinely, both for our flooding as well as the drought mapping that we provide to people like Jerry when they're trying to do decisions on the Indiana drought. So COCORAS has been one good thing that has been helping us. On the flip side, we don't have many measurements out there to understand what is our evapotranspiration or the water loss naturally occurring. Most of the ET sensors, as we look at it, are dwindling away. And so one of the things we started doing was setting up a ET monitoring network so that we can start coming up with some models and we can get a good estimate about the water balance in terms of the rainfall and ET loss. And that's something we have been doing. Ken and others have been going and setting up these sensors over the last 3 years. And I think we now have a good climatology about the ET, which is the evapotranspiration, not the extraterrestrial outcome that we have here. We're typically looking about developing models that can be put up into a GIS mode and then transported to the DRINET portal as we go. One of the impact I would say that DRINET has had was that Carol mentioned that when we started this project, the state of Indiana was using Palmer Hydrological Index, in trying to come up with the estimates of drought. At that same time that the DRINET project was initiated, the Indiana Water Shortage Task Force was initiated by the governor, and Jerry and others were involved, and I was involved in it. And one of the outcomes that we came up with as a part of this assessment was a project that Jam, who is sitting here, she led, in trying to understand the different drought indices and how they behave in Indiana. And we could come up with a recommendation about using the standardized precipitation index and the drought monitor and some of the rules by which drought could be declared in Indiana, and how we can know that we are out of a drought in Indiana. So some of those things that came through. Speaking of tools that are being developed and being made available, We are working and we have a land data assimilation system that has been set up on the portal that provides us with a 4-kilometer resolution, spatial resolution, soil moisture, soil temperature product that is available as part of this multi-year decadal kind of system that is helping us look at a water balance into the mode of things. As we start looking at this land surface data or the soil moisture, soil temperature data, it allows us to start looking into a couple of questions that we are posing. One is, why do we have droughts? Yes, we have droughts because it's not raining, but why is it not raining? I mean, there could be the blocking heights that were talked about. The other could be the recycling that we have. There's not enough moisture, and so we are not getting enough trigger mechanism. And so we are trying to understand the relation between the cloud depth and the cloud heights and the drought conditions. So are droughts feeding themselves in terms of creating them? That's something we're trying to understand. And it looks like under very dry conditions, mainly drought conditions, there is something happening atmospherically. Let me also point this out quickly. One of the features, and there is a poster that will be available in the next room, that we are seeing a very strong relation between droughts and poor air quality, particularly dust. So with the satellite aerosol optical depth data, you can start seeing some good relation about drought impacts in terms of the atmosphere. So it will be interesting to see if we can use aerosol optical depth as one of the indicator going towards the drought conditions that we look at. And that's a feature we are starting to look into more. As we started looking at the vulnerabilities of different regions with drought, one of the features that we were most interested was what happens in the urban areas. And urban areas are definitely different in terms of both the rainfall availability and the resilience that we have. And in fact, this might be of interest. If you look at the tornado hotspots in Indiana, they are just south of the urban area. You can note it over here. This is a tornado hotspot, which is the south of Indianapolis region. And we're trying to understand why this happens. And clearly there is something that is happening at a very local scale, meaning the urban areas are changing some of the storms and creating a tornadic signature perhaps and causing more intense rain. So the question that was being posed is, can we use this kind of information as a city planning tool and provide this kind of information to the policymakers, for instance? So we have been working with a visualization-based tool. This is the computer science part of the DRINET, where the idea was that can we come up with a simple interface that a city planner can come up and mark a region and say, okay, let's make this region green, or let's make this region a more of a reserve park, and what could be the if-then scenario of such a thing. Now within the models, we not only need this greening, we also need information on where are the buildings going to be taller, how are the buildings going to change, what are the albedo and other factors. And so there were rules that were being created and a nice visualization created which could be imported back into the weather model then. And so on the basis of that, so this is the exercise that was taken, for instance. This is the grids with the different land use. You can green it up by saying this area within the southwest part of the region, I'm going to make more greener, and that could change the layout of the buildings, and that could change the environmental feedback in terms of the coupled regional climate assessment for that in terms of the rainfall, temperature, humidity, and so forth. We could come up with more such scenarios, and they're indeed available, but if you want to sum this up, you want to, some of the key future directions that I think we would like to get your feel from based on the interactions we are getting here, and something we could discuss into the panel, is where do we go from here? I think the key points that seem to be evolving is that we still have a long way to go in terms of the drought characterization, particularly with regards to uncertainty representation. We are jumping between drought category 1, D1 to D2, when we know there is a threshold that we ought to meet. And so that uncertainty within whether we are in a D1 or a D2 category, how do we blend that information will be of interest. The quantification aspect, a beautiful weather or a real bad drought, that feature is probably much more of an issue when we are looking at the mild drought cases or the moderate drought cases. The issue of environmental impacts, both on the air and water quality, clearly we are just scratching on the surface at this point, and I think there's much more that we can start looking at, particularly from the southeast US. You can see there could be an ozone feedback that can start coming up, the particulate matter having a feedback back into the whole environmental aspects that we can look into. Indrajit also mentioned about the water quality aspects that are starting to show up. The big focus that we are stressed at this point is how do we incorporate economic data, some of those non-traditional data sets that are very hard to get, public health data, and perhaps that could be something we would love to hear some strategies you guys might have in terms of building that in. But we are trying to come up with a focus on an urban resilience because that's where majority of our focus is, and how can we come up with strategies related to that and agricultural resilience and so forth. The role of communicating this uncertainty is developing better mapping tools and even engaging extension and other communities in terms of what we are trying to develop. For agriculture, extension comes up as a right partner. What should we do different if you are trying to relate with an urban environmental setup? Are there different kind of managers we should start looking into and so forth? So I'll leave it at this particular side, and I know by now you must be ready for your break, so I will pass it on to JS. Thank you.
All right, I think we are already 15 minutes